Hello friends, so picking up from last week, we had this setup that had two coils and we wanted to use it to generate a rotating magnetic field. However, we realized that the setup was pretty limited since it didn't provide continuous power to the motor. There were points where we were literally just applying nothing to the coils. And this is where the other two sets of coils come in. Now, even when the rotor is parallel with one set of coils, the other coils have to do work to keep the rotor moving. For example, when phase 1 is at 0, phase 2 and phase 3 will be doing some work. So basically what's happening is that we have 6 coils that are 60 degrees electrically out of phase from each other. But like we said before, A and A prime are the same wire, or the same signal, just wrapped around the other way. So really all we care about is our A, B, and C phases, which are all 120 degrees out of phase with each other. In theory, we'd want an infinite number of phases, but this is impossible. More phases will allow us to create a smoother gradient, but this means more hardware and more software. Not to mention, every single phase would need wires coming out of it, which would create mechanical limitations as well. So 3-phase is basically the industry standard for this kind of thing. Motor designers do have a bunch of tricks they can use to create a smoother gradient, and in real life you'll never actually see a motor with just 6 coils. In many cases, you'll find multiple sets of A, B, and C's and overlapping coils. However, for the sake of motor control, this representation of the motor will work just fine. So the type of motor I just described is called the synchronous motor. What this means is that the stator is always in sync with the rotor, and they have to be. If the stator starts spinning faster than the rotor, it'll cause the rotor to freeze up, since the magnets won't be pointing in the right direction anymore. The most common example of this type of motor, despite its name, is actually the brushless DC motor. These motors are super common in relatively small applications, like power tools, RC planes, and a lot of electric vehicles. An important thing to note is that while in my examples I put the stator on the outside, this isn't necessarily true. The stator can be on the inside or the outside, as long as it isn't the one that's spinning. And we don't want the stator to be spinning because we have coils wrapped around it, and rotation and wires don't go well together. There do exist rotors with windings, but these are rare for battery-powered applications. In smaller form factor motors, the stators actually tend to be on the inside, and my guess is this is because you can fit more magnets on the rotor if it's on the outside. But as we start to scale it back, it typically flips back the other way, such that the stator is on the outside. And I'm assuming this is mainly to limit centripetal force. Objects that are rotating at really high speeds have a tendency of exploding. The smaller the radius, the lower the force. Check out this really cool build by Laimer. He 3D printed an entire motor, and he included a bunch of build information and CAD files as well. And in general, synchronous motors tend to be rather power dense, which makes them really good for small scale applications like power tools and such. However, one issue is that these permanent magnets can become really pricey, especially with really big motors. And this is where the second type of AC motors comes in, the asynchronous motor. So this motor relies on something called Lenz's law. And if you've ever dropped a magnet down a copper tube, you might notice it slows down a lot. This is because of Lenz's law. What's actually happening is that the magnet is inducing a current in the copper, which in turn generates a magnetic field that opposes the initial magnetic field, which allows the magnet to slow down. In this case, we're using the induced magnetic field to effectively generate a magnet in the rotor. This happens to be really cost effective since there's no motors, but it is a little less efficient. These actually happen to be the most common types of motors, but we don't really see them in commercial applications. They're usually found in factory type settings. However, the Tesla Model S does use an induction motor. An important thing to note is that the asynchronous motor, the stator and the rotor will never be at the same speed, and this difference in speed is known as slip. Electroboom has a couple of videos describing the differences between a bunch of different types of motors. Alright, so we talked about a whole bunch of different things over the past 2 weeks, so let's wrap things up. Why do we need a controller in the first place? Well, in our design, we're working with a battery as our power source. A battery is a DC source, which we need to convert to 3-phase AC to drive our motor. So the primary function of the controller is to convert from DC to 3-phase AC. But we also have a bunch of secondary requirements. It's not just enough to be able to power the motor, but we also want to be able to control the speed, since we don't always want to be going at max speed all the time. To do this, we need some kind of control loop. Furthermore, in the case of a synchronous motor, we have to monitor the position of the permanent magnet so we can provide the correct signal at the correct time. This also has to be factored into our control loop. Finally, we also need to implement some safety features. Chances are your battery pack already features a battery management system, but we'll want to implement some similar features on our controller. These features will act to protect the motor, the controller, and the battery pack. So now that we have a general understanding of what our controller needs to do, we can start to draw out the general motor controller topology. This will cover every major block we need in our controller, both in hardware and software, that we need to meet all these requirements. That's all for today. Tune in next week where we'll do just that.